So, hi everyone, welcome to the post contest discussion of the Codeforces Round 986. I am Abhinav and this is TLE Eliminators. So, let's get started with our first problem, which is Alice Adventure in Chess. Okay, so Alice is trying to meet up with the Red Queen in the countryside. Right now, Alice is at position 0, 0, and the Red Queen is at position A, B. Alice can only move in four cardinal directions: north, east, southwest. So basically, if it's north, he moves y plus 1. If it's east, x plus 1. South, y minus 1. West, x minus 1. Okay. Now, Alice's movements are predetermined. She has a string S representing a sequence of moves that she performs from left to right. Once she reaches the end of the sequence, she repeats the same pattern of moves forever. Can you help Alice figure out if she will ever meet the Red Queen? Okay, so basically Alice has some sequence of moves, okay, which is represented by this string. So she would just repeat this sequence again and again infinite times. Okay, so if she would start with the coordinate 0, 0. Okay, if it is north, she moves one position north, then a north again, then east. Okay, and then sequence is repeated again, then again north, again north, then east. So north, north, east, north, north, east, it would be repeated. So if this is the string, then this sequence would be repeated again and again. This way Alice would move, and we just need to determine whether he would reach the position A comma B, N A B. So this is A comma B. So whether at any point he would meet the at this position, which is the position of the queen, okay, A comma B. So whether he would ever reach that position or he would never reach that position, we need to answer yes or no. Okay, so what we can do here is, okay, let's see this test case. So here you can see that what we are given, that we are given, like, you can take it as a coordinate axis. Okay, so currently Alice is at point 0, 0. This is point 0, 0, and this is N, A, and B. So Alice wants to reach this point A, B. Okay, he wants to reach this point. There is some 1, 2, so 2, 1. Okay, this is the point where Alice wants to reach. Currently, he is here. And what would happen? This is the sequence of moves that would happen. Okay, so C is here. First, she would move one position north. So she moves one position north. She reaches 0, 1. Okay, this point. Then again north, she moves one position north. She reaches 0, 2. Okay, then east. So one position east, she reaches 1, 2. Okay, then again east, one position east, she reaches 2, 2. Okay, then south, so one position south, she would reach 2, 1, which is the position A, B. So here we would say yes, she has reached this position at one particular point in her movement. Okay, let's say if this was not our point, okay, our point was, let's say the point where Alice wants to reach was 3, 1. Okay, so after this south movement, C is at 2, 1. Okay. Then C would move one west and would reach basically 1, 1. Okay. So this sequence would finish. Then again, the sequence would start from the start. Okay. So again, from here, she would move north, then again north, then east, then south, then west. Okay. She would reach here. Then again, the sequence would repeat: north, north, east, east, south, west. Okay, so like this, if it is repeating, you can see that he would infinitely go somewhere here and would never reach this point. Then in that case, we would answer a no, that C would never reach this point. Okay, so basically that only we need to find out. And if you look at the constraints of the problem, then A, B, and N all are up till 10 only, and there are just 500 test cases. So like for each test case, if A, B, N are up till 10 only. Okay, so at max in our coordinate, we would get a point, let's say 10, 10. Okay, at max, it would be 10, 10 far from this point. Okay. And in every cycle, okay, so at max, how many times do we need to repeat this cycle and check? If you are doing just the simple brute force approach, just repeat this process and keep checking. So this string is of length 10 at max. Okay, and this cycle need to be repeated how many times maximum? Okay, so after doing something from an initial point, after one cycle of operation is done, she would reach at some different point. Or if she reaches the same point after one cycle, then after every cycle the same thing is repeating, so there is no change. Okay, so like if in this cycle, let's say something like this is happening, if the point a comma b is covered in this cycle, then in the first cycle only it would be covered. And if you are reaching the same point at the end, then after one cycle, two cycle, three cycle, it doesn't matter. If in the first cycle it's not reaching, then the same path is getting repeated, so there is no change. So we just need to check one cycle if the ending and starting points are the same. And if they are not same, that means if we start from some point, then after the cycle at least there is one movement to the right or to the left or to the up or down. At least one movement is there. So like at max after 10 movements we would reach this point, if we have to reach this point. And like till where do we need to check? It may happen that after some movement you may reach some point here, and then in the next cycle in some half movement you reach this. Okay, so if you have to reach 10 comma 10, at max you would have to check till 20 comma 20, not more than that. So I think if you repeat this cycle 20 times, that would be enough. If even after 20 times it's not happening, then it would not happen. For safety purpose, you can do it 100 times, or even till 10 to the power 4 times you can do, because there are like T's test cases, only 500 test cases. You can run a loop up till 10 to the power 4, 10 to the power 5. That would also be fine. So just do the brute force approach, run this iteration like 100 n times. Okay, so 100 times just run this, that would be more than enough. And if even after 100 times you are repeating this sequence 100 times, still you are not getting a comma b, that means you would never get a comma b. Okay, I hope this is fine to you. Like if you want to calculate exactly, like as I told that 20, it means, why I told 20 was because at max you want to reach 10 comma 10. Okay, and if you start from here, and one case is after the cycle, the point from where you start, you end up there only. So for that case, just checking in one cycle is enough. Okay, if it is not the case, you are starting from this point, that means you are ending at some different point after the cycle. Okay, but in between the cycle you may go somewhere and then end up here. Okay, so let's say you went somewhere and you end up here after the first cycle. Okay, then this thing would be repeated. You went somewhere, end up here. You went somewhere, end up here. You went somewhere, end up here. Okay, so after like 9 cycles you would reach, let's say 9 comma 9. Okay, then in next cycle you went somewhere and you end up here. Okay, but let's say you had to reach 10 comma 9. Okay, not 10 comma 10. Then you reached here, but it may happen that during the movement you are going some back and then coming here. So like till here, if this is repeating, this was not coming, but it may happen when you are at 20 comma 20, then you turned back and reached, like let's say this point 10 comma 9. Okay, like in some 18 comma 19, or from that point you may reach this point and then go back. So like just the upper bound that I was giving was 20, because in any cycle at max you may travel back 10 back, or that is the maximum, like, and the length of n is also till 10. So in one cycle you may at max travel back a length of 10. And in total, if you like if you have traveled till 20 comma 20, then you may travel back a length of 10 and reach this point. That's the maximum. After that, if you are traveling above 20, then even if you come back, you won't come back to a value less than 10. Okay, that's what I was trying to say. Yeah, if you have reached 20 comma 20, there's no way that we can travel back to 10 comma 10. That's what I wanted to say. Okay, so I hope that is clear. So if you look at the code, like the constraints were so small, so like you can just take any upper bound. I took 100, and you can like take, if you are not able to get what maximum limit you need to take, just take a very big limit. Just take 10 to the power 4 into n. That would also be fine, because multiplied by 100 test cases, like you can go up till 1e8 in 1 second, 1e8 operations. So 1e4 into n is 10 into 500 test cases, it would be 5e7 only. Okay. So even 1e4 is okay. So, but the requirement was till 20 only. For upper side, I am taking 100. This was my code, which is accepted. So, so what I'm doing is I'm just running a loop up till 100 times n. I is going from 0 up till 100 times n. Okay. I've initialized my x and y with 0, 0. Okay, initially I'm at point 0, 0. So if x is equal to, if at any point I would first check if x is equal to a and y equal to b, that means I have reached the point a, b, then I print yes and just return out. Okay. And if I have not reached, then I'll perform the operation. Now I'll check s of I mod n. This why I'm doing mod n, because when I is up till n, so mod n would be s of I only. After I is equal to n, then n mod n would give me 0. Okay, so the sequence would keep on repeating from 0, 1, 2. If I'm going to n, n plus 1, n plus 2, then mod n would give me 0, 1, 2, 3, 4. So if I have to cyclically repeat the sequence, then I just take mod n in the index. So how many times we have to take, run the loop till there, and s of I mod n gives me the change that I have to do. So if this is equal to north, I do y plus plus. If this is equal to south, I do y minus minus. If it is east, I do x plus plus. Else, I do x minus minus. I hope this is clear to you. So then even after repeating 100 n times, if I don't get a yes, then I print a no. Okay. I hope this code is clear to you. Its time complexity would be, okay, I am running for each test case. For each test case, I'm running 100 n times. Okay. So 100 into 100 n for each test case. Okay. There are 500 test cases, n is up till 10 only. This would go 500 into 100 into 10 would be approx 5e 1, 2, 3, 4, 5, 5e5 only. Okay. So you could have also taken two more zeros so to make it 5e7. That was also fine till 5e7. So I hope this problem is clear. We can move to the next problem.
Yes, sir, clear.
Okay. So let's move to the next problem, which is problem B. Alice adventures in permuting. So Alice mixed up the words transmutation and permutation. She has an array A specified via three integers n, b, and c. The array A has length n and is given via ai is b times I minus 1 plus c for I from 1 till n. For example, n is 3, b is 2, c is 1. Okay, so an array is defined by three values n, b, and c. Okay, so how is it the array is defined? That means the array would have size of n, so 3 characters. And what would be the values in the array? The values would be, for start with I equal to 1. So with I equal to 1, 1 minus 1 is 0. So 0 times b plus c, then 1 time b plus c, then 2 time b plus c. That's what. So if b is 2 and c is 1, so 0 times 2 plus 1, 1 times 2 plus 1, 2 times 2 plus 1. Okay. That means you start with C, then add a plus B. You start with 1, add a plus 2. It becomes 3. Again, add a plus 2. It becomes 5. Again, add a plus 2. It becomes 7. That sequence would continue up till we have n elements. That's what the definition means. Now, Alice really enjoys permutations of 0 to n minus 1 and would like to transform A into a permutation. In one operation, Alice replaces the maximum element of A with the MEX of A. In MEX is the maximum exclusive, minimum exclusive character. So the minimum value in the array which is not present is called max. If there are multiple maximum elements in A, Alice chooses the leftmost one to replace. Can you help Alice figure out how many operations she has to do for A to become a permutation for the first time? If it is impossible, you should report it. Okay. So what we need to do is you are given three values N, B, and C. Okay, let's see what we need to do. So you are given three values N, B, and C. Okay, so these three values define an array. How is your array defined? So the array would be AI is equal to B times I minus 1 plus C. That's the definition of my array. Okay. So that means what it would be. The first element will start with A1. So it would be 1 minus 1, 0 times B plus C. So it would be C. The first element would be C. Then it would be 1 time B plus C. So C plus B. Okay, then 2 times B. So C plus 2B. Then 3 times B, C plus 3B. This would continue up till we have n elements. Okay, so basically that definition means this. If you are given NBC, you would construct an array like this. Start with C, then C plus B, then C plus 2B, C plus 3B, up till we have n elements. Okay, so that is the array A that we are given using just three variables. Now, in this array A, okay, let's take N, A, and B. Let's take N is 5, A is 2, B is 3. Okay, let's suppose. So what array A do we get? Okay, this is the array. So what array do we get? Okay, sorry, B and C. B and C. Okay. So what array do we get? Is you start with C, which is 3, then keep adding 2. So 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 2 is 9, then 10, until we have 5 elements. So 1, 2, 3, 4, 5, 5 elements. Okay. So this is the array according to the definition for these values. Okay. Now, once we have got this array, what we need to do in this array, you need to find out how many operations do we perform to convert this array into a permutation of size n minus 1. What do you mean by permutation of size n minus 1? That means if n is 5 here, okay, if n is 5, a permutation of size n minus 1 should have all the values from 1, 2, 3, 0, 1, 2, 3, 4. So from 0 till n minus 1, if all the values are present once in this array in any order, that means it's a permutation of size n. Okay, so you need to convert this array into an array having all the values from 0 to 4 once. Now, in every operation, what do? You select the maximum element in the array. Okay, sorry, after 9, we should have an 11. You select the maximum element in the array and replace that with the MEX of the array. Okay, what do you mean by MEX? MEX means the minimum exclusive element. It means the minimum element which is not present in the array, starting with 0. Okay, so if you check, is 0 present in the array? No, it is not present. So your MEX would be 0 here. Okay, so here in the first operation, the maximum element is 11, MEX is 0, so 11 would be replaced by 0. Okay, now in the next operation, what would happen? The maximum element is now 9. What is MEX in this array? The For MEX, we would check whether 0 is present. Yes, 0 is present. Whether 1 is present, 1 is not present. So 1 is your MEX. Okay, so replace 9 with 1. Okay, then again take the maximum element, which is 7 here. Okay, check what is the MEX. So 0 is present, 1 is present, 2 is not present. So 2 would be your MEX. So replace 7 with 2. Okay, then check the MEX. Oh, now the new greatest element is 5. Check the MEX of the array. MEX 0 is present, 1 is present, 2 is present, 3 is present, 4 is not present. Okay, so replace the greatest element 5 with a 4. Now, after this, what we have? We have 0, 1, 2, 3, and 4. All the values from 0 till n minus 1 is present here. So this is a permutation of size n. Okay. So once we have got a permutation, we say we are done. Now you need to just find how many operations did we perform to get this permutation. Here in this case, you can see 1, 2, 3, 4. 4 operations were performed. So for this test case, our answer would be 4. Okay. I hope you understood what we need to do. Now, how can we do it optimally? If you one by one perform the operations, then what complexity it would take at max? Like if you want to get uh, a a permutation of size n. Okay, at max there would be n operations performed. So if you are performing the operation every time n times, okay, you would go order of n. Okay, and for finding the MEX again n would be required. So you would go order of n square, or even if you reduce the optimize the MEX finding way, it would still go order of n if you do the brute force. And you can look at the constraints. N is 10 to the power 18. A and B are 10 to the power 18. So you cannot do the brute force. Even an order of n, you cannot do. So you need to find the answer in some. You can see if there is 10 to the power 18, it means in some order of 1 only you need to find, or maybe log n at max. Okay. So how do you solve this problem? So you need to just find some formula through which you can find out quickly the number of operations you would do. Okay, so let's see. Like for this case, if you analyze properly, then what is happening? The maximum element gets replaced with 0 because 0 was not present. Okay, then the maximum element replaced with 1 because 1 was not present. Then next maximum get replaced with 2 because 2 was not present. Next 5 get replaced with 4. Okay, not 3 because 3 was already present. So this 3 thing was skipped. 3 was present, so no need to replace it. So the next maximum was replaced with 4. Okay, now we got 4. 4 was our n minus 1. It was 4. So once we have got till n minus 1, we stop there. We already have a permutation. Okay, so the number of operations performed, if you analyze carefully, was like at max we would need n operations for 0, 1, 2, 3, 4. Okay, like 5 operations would be required if we are doing an operation to get to 0, 1, 2, 3, 4, all of them. But 3 was already present, so you required only 4 operation, which is 5 minus 1. So I can say that the number of operations would be, okay, in the worst case it would be n, that all the values are required by operations only. From n, what you can say that number of operations required would be n minus the number of values already present. Here there was only one value already present, so you did n minus 1. Okay, if there was two values already present, if let's say here we started with c is equal to 1 maybe, okay, then we would have started with 1 comma 3, then 5 7, and till 9 we would have. Okay, then this 9 would be replaced by 0, 7 by 2. Okay, 9 would be replaced by 0. Then we already have a 1, no need to replace. 7 would be replaced by 2. Okay, then we already have a 3, no need to replace. 5 would be replaced by 4. So here you can see only 3 operations were required because 1 and 3 both were present in the array, which were required in my final range of 0 to n minus 1. So I can say the number of operations would be n minus number of values in the range from 0 to n minus 1 already present. Okay. So like this we can write that this would be our final answer, that like for a general case, we can see that we would have always have an array like this. We would start with C, then C plus B, then C plus 2B, C plus 3B. Okay. So if this if this B is some, let's say we would always move in some multiples of like B only. Okay. A C is some constant. Let's say C starts with some 4 and then we do a plus 2 or a plus 3. Okay. If we do plus 3. So these would be some big values only. Okay. In these values, we just need to find how many values are from 0 to n minus 1, which are present already. So just subtract that. If you just subtract that, you get your final number of operations. Okay. Like because these values would definitely be bigger. So how do you find this thing? The number of values in 0 to n minus 1, which are already present in this sequence. Okay. So this was, okay, let's find this thing. I hope this is clear why we wrote this formula. Okay, there would be one edge case where this would not work. We'll discuss that. Okay, for now, we are supposing that this is correct for any B and C. We are writing that the number of operations would be n. Yeah. Are you asking something? Okay, so what we are telling is the number of operations would be n minus number of values in the range from 0 to n minus 1 that is already present. Okay, so for those we won't need a replacement. For all the remaining values we would need a replacement. Now how can we calculate this? Okay, so if you look, like, let's draw the numbers on a number line. You start with 0, then you have 1, then you have 2. Okay, likewise you have up till n minus 1. Okay, and you would have more values also. So you need to get each value from 0 to n minus 1. And how is the array? The array is of some kind. This, you start with some c. Okay, array is somewhat like this. You start with some c. Okay, and then you move to some c plus b, then you move to some c plus 2b. Okay, then some c plus 3b. Likewise you move up till c plus you can say n minus 1 times b. Okay, so the array is something like this. You need to find how many values in the array are in this range from 0 till n minus 1. Okay, so how many values would be in this range is, if you look at C, basically before C, less than C, we won't have any values. Okay, so the values would only start with C. So whatever is the value of C, from C to n minus 1, how many values we have? Like in this particular case, how I have drawn, there is 1, 2, and 3 values. Okay, but it won't be the same always. It would depend on the values of C and B. So how can we calculate that? If you start with C, then from C till n minus 1, how many values are present? Because you would start with C, then you would move. This gap would be of size B, this gap would be of size B, this gap would be of size B. So if you are moving in gaps of size B, 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 so how many values at max can adjust in this range? That you can say that, first of all, the size of this range. Okay, what I would write, what is the size of this range is from C till n minus 1, how many values we have? From n minus 1, if we subtract c minus 1, we would get the number of values here. So it is n minus 1 minus c minus 1, which is actually n minus c. Okay, so here in total we have n minus c values in the here. Among them, how many are in the array? Okay, so all the values in the array are separated by a distance b. So if from n minus c, okay, so number of values in array, it would be n minus c upon divided by b, the seal of that we can say. Uh, is it clear? Like from c till n minus 1. Okay, let's take the example. If I have, if let's say I have, in that case only, where n is 5, c is starting with 1, b is 2, let's say. Okay, so then what we can say in our number line, it is 0, 1, 2, 3, 4, 5, 6, 7, 8. In the array, what we have? In the array, we have 1. So 1 is present in the array. Then 1 plus 2, 3 is present in the array. Then plus 2, 5 is present in the array. Then 7 is present in the array, 1, 2, 3, 4. And then 9 is present in the array. These values are present in my array. Okay, these are the 5 values present in my array for c equal to 1, b equal to 2. I need to find how many values from 0 till n minus 1, which is 4. From 0 till n minus 1. From 0 till n minus 1, 4. How many values in this range are present in the array? Here you can see there were 2 values. How do we determine this 2? We say that this is our C. So we need to find in the range from C to n minus 1. So from C to n minus 1, we would say we have n minus C upon B, seal of that values. What is that? So n, in total we have n minus C values, which is 4 minus 1. Okay, so here we have 1, 2, 3, 4 values, like n is 5. Okay, n is 5. So we have 5 minus 1, 4 values here in this range from n minus 1 till C. And among those 4 values, the values are separated by a distance of b. So we divide by b, which is 2. So we divide by 2. and we take the seal value because it would be 4 by 2 here we would get 2 only. Okay, but if n was, let's say, one more, if n was 6 here. Okay, so if n was 6 here, then we would have been checking till 5. Okay, so for this range, if you want to find, you can see there were three values. How we got three values? It was n minus c is 6 minus 1. So among these five values, if we are having values separated by a distance of 2, then divided by 2, we got 5 by 2. Okay, so if you take the floor value of 5 by 2, that would be 2. But actually, you can see there are three values. Okay, so it means you need to take the seal value. Okay, so we would take the seal of 5 by 2, with which we would get a 3. I hope this formula is clear to you. So we would say our final answer is, so this thing is actually n minus c by b, the seal of n minus c by b. So I would say our final answer is n minus c upon b, the seal of that. Okay, so we have got a formula to determine our final answer. Okay, so I hope this is clear to you. Now, the only case where this would fail is when b is equal to 0. Okay, so what if b is equal to 0? Then what would happen? Our array would be something like this: c, then c plus b would be c, then c, then c. Okay, so the array would only have c, 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 c. So in this case, like, dividing by b anyways is dividing by 0 is not possible. So from this only you can say that for b equal to 0 case, we need to handle separately. So what is actually happening here? Okay, so let's separately handle this b equal to 0 case. So what is happening here is, in the array we have c, 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 c. So let's take n is some 5 and c is, let's say, 3. Then what would happen? Our array would be 3, 3, 3, 3, 3, 5 times. Okay, so now how many operations would be performed? If you look, the maximum value here is 3 only. So it's said that replace from the left side. Okay, if there are multiple maximum values. So this 3, okay, it doesn't matter actually. You need to just have all the values from 0 till n minus 1. The order in the array doesn't matter. So you replace left side, right side. It doesn't matter actually. So let's replace this 3 with the MEX. MEX here is 0. So it would be replaced by 0. Now here the new MEX is 0 is present. So 1 is not present, replaced by 1. Now the MEX is 2, replaced by 2. Now you can see that 0, 1, 2, and 3 is also present. Now the MEX is 4. Okay, so 3 would be replaced by 4. Now you can see we have got a permutation from 0, 1, 2, 3, and 4. All are present. So we got a permutation. Here in 4 operations only we got. Okay, so in n minus 1 operations only we got, because this C, one of the 3 was already present. Remaining we got using the operation. So in n minus 1 we got if this C was in the range from 0 till n minus 1. Okay, what if this C was, okay, what if, let's say, we take n is equal to some greater value 7, and for the same C is equal to 3, what is happening? Let's see. We have 3, 3, 3, 3, 3, 3 and 3. 1, 2, 3, 4, 5, 6, 7. Okay, here if you see, this 3 would be replaced by 0, then replaced by 1, then replaced by 2. Okay, now the new MEX is 4. So this would be replaced by 4. After that, the new MEX is 5. Okay, 1, 2, 3, 4, 5 all are present. So, but the new maximum value in the array is 4 now, not 3. Okay, that you have to keep in mind. So the new maximum array in the maximum value in the array is now 4. So 4 would be replaced by MEX, which is 5. Okay, this would happen. After that, the MEX now is 4, because 4 is now not present. It got replaced. So the maximum value 5 would be replaced by 4 now. Now again, the MEX, the maximum value is 4 and MEX is 5. So 4 would be replaced by 5. So this cycle is going to continue: 5 replaced by 4, 4 replaced by 5, 5 replaced by 4. So it would never form a permutation of 0 to 6. Okay, 0 to n minus 1. This permutation would never be formed, because 6 we would never get a 6. This cycle of 4 replacing 5 and 5 replacing 4 would continue here. So for this case, we can see we would have to print -1, that we can never get. Okay, so what is the condition? When do we get a -1 in this case? So we can say the condition for it is, here you can see that when n was 5, c was 3, we were able to replace it. Okay. What if n is increased to 6? Okay. So when n was increased to 6, we have one more 3. Then this 4 getting replaced by 5 would happen, and this 5 replaced by 4, this cycle would continue. Okay, but even if this 4 gets replaced by 5, okay, this cycle would continue, and we would never get a permutation where all values from 0 till 5 are present. This 3 is present two times. Okay. Now, once this 3 get replaced by the 4, the remaining two threes would never get replaced, because we have a 4, it would be replaced by 5, 5 would be replaced by 4. This sequence would happen. So we got two threes remaining and they can never be replaced. So then we would print a -1. So what is the condition? If we have many C's, then we would basically print -1. So if this n is very greater than C, then we would print -1. But what is the exact value that it should be greater? When we are left with at least two C's. Okay. So basically here, this was the case for n equal to 6. We can see that we got a -1. For n equal to 5, we were getting our answer. Okay. Some answer we were getting. But for n equal to 6, we got a -5. Basically, uh, if you have n values, okay, and then if C is equal to, okay, there can be two cases. If C is equal to n minus 2, okay, so when n was 5 and C was 3, it was this case. Okay, so for this case, only 1 3 was left, and we were able to do it in n-1 operation. Okay, so like let's just divide it into, when C is equal to n-2, the answer we got was n-1. Okay, so like you can see when n was 5 and C was 3. Okay, for any general case, if you have C is equal to n-1, n-2, okay, that means we have C n times. Okay, and this C is actually n-2. So till n-3 there would be replacements. Okay, then n-2 would be covered by C, then the replacement would make it n-1. Okay, so basically after the next replacement we would have everything from 0 till n-1, when this n-2 is replaced by n-1. So in this case, in n-1 ways we are able to get. You can see from the example of when n was 5, you were able to get in 4 operations. And if C was equal to n-1, then what is the case? So if we have, let's say, n equal to 5 and C equal to 4, okay, or for C equal to 3, if n is 4, okay, then what is happening? Okay, let's check it below. If n was 5 and C was 4, let's say, okay, then the array we have was 4 4 4 4 and 4. Okay, so this 4 got replaced by 0. Here we have a 1, here we have a 2. Okay, and then here we got a 3. After this it became a permutation here only. Okay, this 4 replacement was not required. 0 1 2 3 4, all we have. In how many ways we did? One replacement was not required, so in n-1 ways. Okay, in 4 operations we did that. So here also our answer was n-1. So for this case, when C was n-1, here also our answer was n-1. Okay. But if C was greater than n-2, like in this case, sorry, it was, if C was less than n-2, okay, which was this case where n-2 was 5, okay, and C was less than that, or in this case where n-2 was 4 and C was less than that, here we can see that at least two threes were remaining or three threes were remaining. So for that, we were not able to do. So for more number of n, basically when C was very smaller than n-2, then we would have -1 as our answer. Okay. And for the remaining case where C is, okay, so either C was less than n-2 or it's equal to n-1, n-2, or if this C is greater than n-2 or C is greater than n basically. Okay, C less than n-2 case is covered. C equal to n-2, C equal to n, and then C would be equal to n or greater than n. So c greater than equal to n. This case is only left. So when c is greater than equal to n, like you can see, if n is 5 and c is 5, that means you have 5, 5, 5, 5, and 5. Okay. So when c is either equal to n or greater than n, then you need to get everything from 0 till n minus 1. So if c doesn't fall in this range of 0 to n minus 1, that means we would need all the replacements. All the c needs to be replaced. So basically this would be replaced by 0, then a 1, then a 2, then a 3, then a 4. So all 5 operations would be required. So for this case, the answer would be n. Okay. So I hope this case thing is clear to you. For the case of b is equal to 0. Okay, when b was equal to 0, we would have these cases. Okay, so if c is greater than n, okay, if c is large, n is small, then we would have to do all the n operations. Okay, or if c is still equal to n, it is this. Then if c is equal to n minus 1, then in n minus 1 operations we would do. Or if c is equal to n minus 2, then also in n minus 1 operation we would do. And if c becomes less than n minus 2, then we cannot do in minus 1. We would have an infinite cycle. I hope these cases are clear to you. So we just need to implement this. Okay, so for b not equal to 0, our final answer would be directly this thing. Uh, our final answer would be directly this thing when b is not equal to 0. And b when b is equal to 0, we would have these cases. Okay, so in some if else cases, we can write our final answer. Let's look at the code. Okay, here you can see we took n, b, and c as input. So when b is equal to 0, we handle it separately. What cases we have? So if c is either n minus 2 or n minus 1, our answer would be n minus 1. So if c is n minus 2 or n minus 1, our final answer is n minus 1. Okay. Else, if c is less than n minus 2, I would print a minus 1. So if c is less than n minus 2, I would print a minus 1. Else, I would print n. Okay. In the remaining case, when c is greater than n, my answer would be n. I hope these cases are clear to you. Okay, then I return. So for b equal to 0, my job is done. If b was not 0, I would not return and my answer would be, okay, so here, what's my answer? My answer is n minus ceil of n minus c by b. Now, one way, if you want to write like a ceil of, okay, if you want to write ceil of x divided by y, where x and y are both integers, okay, like in C++, when you divide x by y, when you divide two integers, you get the floor value of them. If you want to take the ceil value, what you do is ceil of x by y is equivalent to floor of x plus y minus 1 by y. Okay, so like, because if you want to do like ceil of 5 by 3, if you want to do, it would be same as 5 plus 3 minus 1 is 2 by 3, the floor value, 7 by 3. Okay, I hope you understand, because 5 was the first value, just like you can understand. 6 by 3 was 6 was a multiple of 3. Okay, 5 was just one less than that. Okay, and if you want to convert into floor, okay, and you add 3 minus 1, 2. Okay, so that would get converted to the next uh, place. Only for the case where it is completely divisible, it was 6, then you are adding only 2. Okay, so then the both ceil and floor would remain the same. So I hope if you know the property, that is okay. Otherwise, you can convert both of them into decimal and take the use the ceil function, and you can do the decimal division and take the ceil function and then convert it into int. Okay, remember to use round there instead of just directly converting int, because some 0.999 may get converted to 0.0. Okay, if you doing through decimal. Okay, another way is to take ceil of two numbers x divided by, you can write x plus y minus 1 divided by y. So that's what I did. I had to do ceil of n minus c by b, which is same as the floor of n minus c plus b minus 1 by b. Okay, this floor value. Okay, these two things are the same. So I did here n minus c plus b minus 1 divided by b. I took this. Okay, and one more thing, this n minus c may become negative also. Okay, so if this is negative and we get finally a negative value, Okay, we won't subtract some negative value and make it greater than n. Okay, so it would be 0 only. If this is negative, then it would be 0. So I just take the maximum. Either if this value becomes negative, then I take maximum with 0, so that I don't get any negative value. If it is negative, it's converted to 0. So I take max with 0. So n minus this seal of n minus c by b, which is written as floor of n minus c plus b minus 1 by b. Okay, so this thing is only written here. Take maximum with 0 so that you avoid the negative. So this is your answer and you print the answer. I hope this is clear to you. So this was the B problem. Like if you look at the time complexity, this is simple if else cases. All are order of one, order of one, order of one. This is simple formula in order of one. So everything is order of one. So you can see my fine time complexity is constant time, order of one. And space complexity is also no extra space, some three variables B, N, B, and C are used. So in constant time and space, we are solving this problem. Okay. I hope this is clear. If there is any doubt, you can ask now, or we'll move to the next problem. Okay, so let's move to the next problem, which is Alice Adventures in Cutting Cake. So Alice is at the Mad Heartless Tea Party. There is a long seed cake made up of n sections with tastiness values A1 up till AN. There are m creatures at the tea party, excluding Alice. So Alice would cut the cake into m plus 1 pieces. Basically, he would partition the array into m plus 1 subarrays. So each subarrays consists of some adjacent sections. So the sum of every basically the sum of the subarray represents the tastiness of the piece of that piece. Afterwards, she would divide these m plus 1 pieces up among m creatures and herself. So m of the pieces would go to the m creatures and one piece would be kept by herself. Okay, her piece can also be empty. However, each of the M creatures will only be happy when the tastiness values of its species V or more. Okay. So for each creatures, they demand that their piece should have at least V value. Alice wants to make sure every creature is happy. Limited by this condition, she also wants to maximize the tastiness of her own piece. Can you help Alice find the maximum tastiness her piece can have? If there is no way to make sure every creature is happy, output -1. Okay, so basically what we are given is that we are given some array. Let's take this test case. Okay, or take this test case. Let's see. So we are given some array A, and we are given some N, M, and V. So what we need to find out is we need to divide this array into M subarrays. Okay, we need to divide it into m subarrays. Sorry, m plus 1 subarrays. We need to divide it into m plus 1 subarrays. So here m was 2. So m plus 1 is 3 here. So we need to divide it into 3 subarrays. Okay, let's say we do some partition here and here. That way we would divide it into 3 subarrays. So do some partitions and divide it into subarrays. Okay. Once we have divided into 3 subarrays or m plus 1 subarrays, then we need to divide those pieces. Okay, let's say I did this type of partition. This is one subarray, this is another subarray, this is another subarray. Let's suppose I divided it into 3 pieces like this. Then for each piece, its tastiness values would be just the sum of that subarray. So for this piece, 1 plus 1 is 2. So its tastiness value of this piece would be 2. 10 plus 1 is 11. So this piece would have tastiness value 11. 10 plus 1 is 11. So this would also have 11. Okay. So basically you can see that we have divided this cake into 3 pieces of having tastiness value 2, 11, and 11. Now we need to distribute among these m plus 1 pieces. M pieces need to be distributed to the creatures and one piece is kept by Alice herself. So for the creatures, the condition is that they should get a piece of tastiness value greater than equal to V. Okay. So every creature should get a piece of tastiness value at least V. Okay. So here V is given 3. That means the creatures should get pieces of tastiness value at least 3. So if you are dividing like this, you would have to give this one to the creature, this one to the creature, because you cannot give this one to the creature because it 2 is less than 3. Okay, so you cannot give. 11 is greater than equal to 3, 11 is greater than equal to 3, so they are okay to give. So these two would be given to the creatures and this would be kept by Alice. Okay. Now, so the piece that Alice keeps, its tastiness value is 2. So you need to maximize this value basically. How do you distribute optimally so that you maximize the tastiness value of the piece that Alice keeps? Here the answer was 2 only. I think in the third test case, 2 was the best possible. Okay. In whatever way you divide this subarray, making sure every creature gets a piece of at least V value. Okay, the maximum you can keep for Alice was 2 here in this case. Okay, so how do you solve this problem? So if you look like, okay, if you look like we have any random array, we would have some array. You need to divide this array into m parts. Okay, and then among those m parts, one of the part would be kept by Alice, remaining parts would be kept by the creatures. Now for the creatures, we only need to just have a part having value just greater than or equal to V. Okay, once value reaches V, we don't need to give some extra value to that part. Okay, it would be better to give it to Alice somewhat. So whenever it reaches V, you have to stop there. But the problem is like, initially many people would be thinking of the binary search approach in this, that you need to maximize the value that Alice gets. So like maybe you can do a binary search approach here, but I got a simpler approach also. But in the binary search, the problem was, if you have fixed that you are in your check function, you would have to check whether you can get, let's say, check X represents whether you can get for Alice, whether you can get a value of X. So like if you fix that you need to get a value of X for Alice, but that X can be in the first subarray, in middle some subarray, in the last subarray, anywhere. And for the remaining subarrays, you need to make sure it's greater than V. So M subarrays should be greater than equal to V and one subarray should be greater than equal to X. That's what you need to make sure. So doing this in order of N was a little bit tricky. Maybe it was possible, but the better approach that I thought was, uh what you finally, how would your subarray look like? Okay, if you see, one of the pieces would be for Alice. Let's say you have some piece, let's say this. Okay, you keep a range from L to R. You assign a range from L to R that this subarray is given to Alice. Then if this subarray is given to Alice, is it possible, like if you just try that, if you give this subarray to Alice, that means before, in the array given before, we need to divide it into subarrays of size greater than equal to V. So how many, you can just determine in this prefix how many maximum number of subarrays you can make of size greater than V equal to V. And in this suffix, how many maximum number of arrays you can get of size greater than equal to V. So the number of subarrays size greater than equal to V here plus here, they should be at least M. Okay, then it would be valid. That's the thing. But again, if you're checking for every L and R, that would go order of N square. Okay, so you cannot go every L and R. But what you can do is, if you look, basically, finally your array is getting divided into, you if three parts. One part, one middle part would be kept by Alice. The remaining prefix and suffix, these two parts would be kept by the creatures. Okay, so you can say that whatever L and R you keep, always you can just represent your final, you can think about your final array like this, that in the middle we have some piece for Alice, and then to the left of it we have some pieces for creatures, to the right of it those are also for creatures. Okay, so what would be the cases? Now in total, you know that from here the number of pieces for creatures and from here the number of pieces for creatures. Okay, so here you would say that if you have, let's say if you have fixed your LNR, then you can calculate that in this prefix how many maximum pieces you can have for your creatures. So you would have X number of pieces for the creatures here in this side, and let's say Y number of pieces for the creatures in this side. So and the condition is that this X plus Y should be at least M. Okay, then it is okay. Or even writing greater than equal to M is, let's write equal to M only. Okay, so that's the condition, that from the start you would have assign X pieces to the creatures, from the end you would assign Y pieces to the creatures, such that this X plus Y is equal to M, so that you assign these M pieces to the creatures, and the remaining in the middle, that value would be for Alice. Okay, so what cases can we have? Now you can determine, like if you start from the start in the array, take the first value, okay, add it to your sum. If it becomes greater than equal to V, okay, till here you would say that one piece. Okay, now start the next piece. Okay, add those values. If it becomes greater than equal to V, you say you do a partition here. Yes, that is done. So if you want to get X pieces, okay, if you fix your X, let's say, if you want to get to X pieces, you can determine the minimum index till where you can obtain X pieces. Same way from the end, if you want to get Y pieces, you can determine the basically the maximum index till where you can get Y pieces. Okay, that can be determined greedily. If you from the start, if you start selecting, let's say uh, you select the first piece, the value was less than V, so you select the next piece also. Now the sum got greater than equal to V, so this whole part is one subarray. Then start with sum equal to 0, select the next piece. Okay, if the sum gets greater than equal to V, okay, then again do the partition, add to your count that one more subarray we got. Okay, so until the time you get X subarrays, the minimum index till where you get X subarrays, you would say that till this index we need. So for X subarrays, we need this index. Same way from the end, if you do, then uh, for Y subarrays, we need till this index. So what all values can X and Y take? Okay, if you look, X plus Y should be M. So either we would have X equal to 0 and Y equal to M, or if X is equal to 1, Y would be M minus 1, or if X is 2, then Y would be M minus 2. Likewise, we would go up till X is equal to M and Y equal to 0. These can only be the cases in general if you look. Okay, in general, if you say that uh, some subarray, some part in the middle is going to Alice, then the number of pieces to the left of L would be X, and number of pieces to the right of R would be Y. So what all values can X and Y take? So either we would have X is 0, we don't have anything to the left of L, that is L is the first index, if L is the first index, L is like in 0 based, in 1 based, if L is equal to 1, if here we have 1 as L, then it means before we have X equal to 0, we don't have anything. Or same, if R is equal to N, here we have R, then after that we don't have anything, so Y is equal to 0. So it would vary. If X is 0, then to the right side we need M values. If X is 1, in the right side we need M minus 1 value. If X is M, then in the right side we need 0 values. Okay, so we can iterate over all these possibilities, and for every possibility, okay, if you have fixed your X, then you can just pre-compute that if you want to keep X equal to 0, what is the minimum L that we can keep. Okay, so for every X, determine the minimum L, pre-compute the minimum L. For every Y, pre-compute the maximum R. Okay, now for every case, when you know the X and Y, then you know the minimum L and the maximum R. Now for the range from L to R, take the sum. So if you have pre-computed a prefix sum, you know the range from L to R, what is the sum. So maximize that sum basically. Okay, so for this case, your answer would be, so you would pre-compute three things. Okay, I hope the approach is now clear. You would pre-compute three things for every X. For every x, you would pre-compute minimum I such that you get you get x uh, x pieces having value greater than equal to v. Okay. And for every y, you would compute the maximum I such that you get x pieces. Here you get this in the range from 1 till I minus 1. In this range, you get x pieces, and in y you would calculate from the suffix. So the maximum I such that you get x pieces greater than equal to y in I plus 1 up till n. Okay. So if you can pre-compute these two things, okay, for if you want only 0 pieces, then I would be 1. Okay, for 0 pieces, you can start with 1. Okay, so like instead of I'll tell it as L, and for this, I would say R. Okay, then it would be more clear what I'm writing. Okay, so for every X, if X is 0, what is the minimum L you can keep? It would be 1. Okay, you can start right from 1. If X is 1, what is the minimum L you can keep? So just have one subarray value having value greater than equal to v. Just after that, keep that L. Okay, so the first L for that, the previous sum is greater than equal to v. Keep that L. That is for x equal to 1. Then for x equal to 2, okay, after that you keep one more sum, one more piece, which gives you value greater than equal to v. Then keep that L for x equal to 2. Okay, I hope this is clear. So that you would pre-compute for every y, you would pre-compute, then you would iterate through all these possibilities. So for whatever x and y, you have pre-computed that for this x I have this minimum L, for this y I have this minimum R. Take the sum from L to R using your prefix sum, which you have also pre-computed. So take the sum from L to R and take the maximum among mx comma that sum from L to R. Okay, if you write that, you can get the maximum. Okay, I hope it is clear. Let's just do a quick dry run so that it's more clear on this test case only. Okay, let's say you have this test case. Okay, let's take a different test case. Okay, let's take this test case. So what I'm doing here is, okay, if this is the array, then this is n, this is m, this is v. Okay, so I need to make sure the pieces are greater than equal to v. So the first, like in v1, just represents v1 of I is the first thing that, okay, like in my code I've written v1, so I'm writing that only. So for every x, what is the minimum L? So that is represented by my array v1. Okay, so my v1 of x basically represents this thing, and v2 of y represents this thing. Okay, that's what I'm denoting by my first vector. So I would say my v1 of 0, what it would be. So first I would compute like that in v1 of 0. It means I don't need to keep anything for x equal to 0. The minimum L I can keep is, I can start with index 1. Okay, so this would be 1. Now v1 of 1. So I'll start from here. Okay, I'll assign v1 of 0 as 1. Okay, then I'll start from here. I'll keep on summing it up until I get 11. So I'll keep a value s is equal to 0. Okay, add a plus 1. Okay, it becomes 1. Check whether it is greater than equal to v. No. Keep adding. Okay, go to the next index, add a plus 1. It becomes 2. Now, whether 2 is greater than 11? No. Keep adding. Add a plus 10. It becomes 12. Now, whether 12 is greater than equal to v? Yes. Okay, so we would say that like till here, this subarray can be one piece. Okay, so which can be given to a creature which have a sum 12. So for v1, for having only one piece, the minimum L we can keep is 4. Okay, so we can start giving Alice from 4. So for v1, I would assign 4, and then again I'll reset my S as 0 and start from here for v2. Okay, so for if you want to have one more piece, then I'll start from here. Okay, so S is 0. I'll add a plus 1. It becomes 1. then again add a plus 1, it becomes 2, add a plus 10, it becomes 12. Now 12 becomes greater than equal to V. So this whole piece need to be kept. So V1 of 2, okay, if you want to give two pieces to the creatures, okay, then we would require how much? The minimum index we can keep is like this seventh index, okay, which is greater than n only. So basically for V2 we would have to keep this L. So basically we cannot have anything for Alice in this case. Okay, this was from the prefix side for every x. Okay, so if we want to keep x equal to 0, then I can start my L from 1. If you want to keep x equal to 1, then I would have to take this piece and start my L from 4. If you want to keep x is equal to 2, then I would have to take this piece and this piece, and after that I would have to start from 7. Okay, so this is done. Now for the V2 of y. Okay, for every y, if we want to compute that, we would compute from the suffix side. From this side we would compute. So for every y, if you want to compute, so I'll say my, okay, this was V1 only. I'll say V2 of 0, that if you want to keep 0 values to the right, if you want to keep 0 values to the right, that means we can start with index 6 only. Okay, so I can start with n basically here. Okay, then I'll again reset this s, keep s is equal to 0. Okay, and start summing up from here. So plus 10, it becomes 10. Is it greater than 11? No. Again, go to the next index, add a plus 1, it becomes 11. Now this 11 is greater than equal to v. So we are okay. Okay, so from the right side, we got this subarray. Okay, so for v2 1, if you want to keep y is equal to 1, so if you want to keep y is equal to 1, that means from the end, if you want to have one piece, then the maximum r we can keep is 4. So from here we can start for Alice if we want to give one piece to the creatures. So this would be 4. Okay, and then again reset your s to 0, start summing up from here. So a plus 1 here would make it to 1, a plus 10 would make it 11. Again, we have an 11 which is greater than equal to v. So this can be our another piece. Okay, so if we divide it into two pieces, the r we can keep is 2. Okay, so we can start from here by giving two pieces to the creatures in the right. So v2 of 2 would be 2. I think, yeah, we can start with r is equal to 2. We would give two creatures, two pieces to the creatures in the right. Okay, then for 3 also we can pre-compute starting with s is equal to 0. Okay, but once we have pre-computed till n, m, no need to compute more. We won't have more than m pieces given to the creatures. Okay, so once this v1 and v2 are pre-computed, okay, also we would pre-compute our prefix sum. Okay, that is the basic thing. We would also compute our prefix sum. So 1 plus 2, 12, 13, 14, 24. Okay, so this prefix sum is also pre-computed. Then we would calculate our answer. Okay, so we will calculate our answer starting for every case. So x equal to 0, y is equal to 2 case. For this case, what would be our answer? For this case, we would take the minimum L we would have is v1 of x, which is 0. Okay, so v1 of 0 is 1. So L equal to 1 we got. R would be v2 of y. Okay, so which would be v2 of 2, which is 2. So R we got is 2. Okay, so basically I'm telling that the right side I'm doing keeping two creatures. So these two creatures would be kept in the right side. This is taken as my R, and left side I have 0 creatures. So this is taken as my L. So L is 1, R is 2. So this piece goes to Alice. Okay, with L is equal to 1 and R is equal to 2, this piece goes to Alice. So if this piece goes to Alice, the value that Alice gets is the sum from L to R. So that can be calculated using the prefix sum array, prefix of R minus prefix of L minus 1. Okay, this way I can calculate. So this sum would be 2 minus 0. Okay, so this would be 2. So for this case, x equal to 2, y equal to 2, my answer is 2. Next, I would move to x equal to 1 and y equal to 1 case. Again, the L I get for x equal to 1 would be v1 of 1, which is 4. The r I get for y is equal to 1 would also be 4. Okay, so from left side I keep, okay, so 4 would be my L and R. So this piece would be taken. This is for left side, this is for right side. Okay, so answer would be sum from 4 to 4, which would be this 1. Okay, so maximize with, here I got 2, here I got 1. Next case would be x is equal to 2, y is equal to 0. For that again, like if you keep 2, 2, v2, this would become 7. So you would get nothing, you would get 0 here. So final answer is the maximum among the three cases. Case 1, you got 2. Case 2, you got 1. Case 3, you got a 0. So the maximum among 2, 1, and 0, it was 2. So your final answer was 2 for this test case. Um, this was the fifth test case, I guess, and answer was 2. Okay, I hope the dry run is clear. Let's quickly look at the code. So first thing I did is, this was just the input part. After that, I calculated my prefix array. So prefix sum. Okay, I've taken 1 based indexing here, my array from 1 till n. Okay, so my prefix sum is also 1 based. So prefix I is prefix I minus 1 plus ai. This way I compute my prefix sum. Okay, now I compute my two vectors v1 and v2. v1 would be from the start. If we have want to keep x creatures, then what is the minimum index from where we can start L? And v2 is from the end. If you want to keep y creatures, what is the maximum R? So for v1, we would start computing. We'll keep s is equal to 0. Now in v1, I would push back 1 because v1 of 0 is 1. Okay, this is fixed. After that, we need to compute. And in v2, v2 of 0 is n. Okay, so this is fixed. After that, we need to compute. Okay, so for the remaining v's, I would start with s equal to 0. I would run the loop s plus is equal to ai. If this sum becomes greater than equal to v, in v1, I would push back I plus 1. Okay, so till index I, if my sum becomes greater than v, okay, then we can start with I plus 1 as a L. So the minimum L would be I plus 1. We push back in v1 and set s is equal to 0. This way v1 is computed. Same for v2, we run a reverse loop starting from n up till 1. Okay, s is set to 0, s plus is equal to ai. If it becomes greater than v, in v2, we push back I minus 1. Okay, so from the suffix till I, if we are able to form y creatures, then I minus 1 would be the maximum R we can keep. Okay, so in v2, we push back I minus 1 and again we reset our s as 0. So this way I compute v2. Okay, so one base case for -1 case is checked if the size of v1, the maximum number of in v1 we would get, like if you start giving it from the start, the maximum creatures that we can have by traversing till the end. If we have traversed till the end and the maximum if the size of v1 is whatever is the size of v1, its last index would be v1 minus 1. Okay, so if the last index is less than m, that means we have not calculated v1 of m because it was not possible to have m creatures till that nth index. So then we would print -1. If v1 dot size -1 is less than m, we would print -1. Okay, and return. So this -1 case is handled. If this case is not there, we have calculated till index m. That means we are able to have m creatures. Okay, so then we won't have a -1 case. Okay, then I'll initialize my answer with 0 for every case where we keep x as I. So I iterate from I is equal to 0 to m. So here my x is I and my y is m minus I. Okay. So I iterate through all the cases starting with x equal to 0, y equal to m, x equal to 1, y equal to m minus 1. Likewise, x equal to m, y equal to 0. So this way I iterate to all the possible cases. Okay, and L would be V1 of X. Okay, so V1 of X, which is V1 of I. R would be V2 of Y. Y is M minus I. So R is V2 of Y. So that way I get my L and R. And my sum from the range L to R would be prefix sum R minus prefix sum L minus 1. This way I get the sum from L to R. And in answer, I take the maximum answer comma sum. Okay, this way I maximize my answer. And I finally print my answer. I hope this is clear to you. What would be my time complexity? Here, this input part is taking an order of n time. Then this prefix computation is taking an order of n time. Okay, so this pushback is order of 1. Then this loop is running n times. Okay, these are order of 1 operations. So this loop is taking n times to pre-compute my v1. Okay, then pre-computing v2 again. This is order of 1 running n times. This would take order of n. Okay, so this is a if condition order of 1. Here I have a loop of running till m, and this is order of 1. This sum is also order of 1 because I'm using just pre-computed values. Okay, so all these things are done in order of 1 time m times. So this would be order of m. Okay, and then finally we print the answer. So basically my final time complexity is order of, you can look, we have n, 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 and here we have m. So an order of n plus m, you can say. And what would be my space complexity? It would be, I'm using just these two extra vectors of size n at max. This prefix sum would have at max size n, array A would have size at max n. So it would be have order of n. Okay, I hope this problem is clear to you. Okay, so let's move to the next problem. Okay, so in problem D, okay, this is an interesting problem. So Alice is playing cards with the Queen of Hearts, King of Hearts, and Jack of Hearts. There are n different types of cards in their card game. Alice currently has a card of type 1 and needs a card of type n to escape Wonderland. The other players have one of each kind of card. In this card game, Alice can trade cards with the three other players. Each player had different preferences for the n types of card, which can be described by the permutation QKJ for Queen, King, Jack. Okay, so there are basically four players. Alice is one of the players, and Queen, King, and Jack are the three other players. Okay, so all of them has some preferences for the n cards represented by a permutation. Okay, so what is the preference is like a player values card A more than card B if their permutation PA is more than PB. Okay, so for if in their permutation PA is more than PB, that means he would value card A more than card B. Then this player is willing to trade a card B to Alice in exchange for card A. Okay, so he can, if he gets a card A in exchange for card B, he is willing to exchange that because his preference in his preference order A is greater. Alice preference are straightforward. She values card A more than card B if A is greater than B. Okay, so if whichever value of the card is greater, then Alice would have greater preference. She will also trade according to these preferences. Determine if Alice can trade up from card 1 to card n subject to these preferences, and if it is possible, give a possible set of trades to do it. Okay, so you need to determine Alice would start with card 1. Can she get to card n by some possible trades? Okay, if it is possible, print a yes along with the trades that she does. If it is not possible, print a no. Okay, that is the question, and n is up till 2 into 10 to the power 5. You need to do some order of n type of thing. Okay, so what we can do here is, okay, let's understand the problem statement first. So you have three players. This is queen, this is king, and this is jack. Okay, and one is Alice. So for Alice, his preferences are straightforward. It's like 1, 2, 3, 4. Okay, 1, 2, 3. For Alice, his preferences are 1, 2, 3, 4. So uh, one has greater value, two has like likewise the greater number has greater value. For queen, king, jack, preferences are represented by these permutation. Okay, how? So let's see. Queen has 1, 3, 2. This is the indexing. Like permutation for queen, we can say this. That means for card 1 has preference of 1, card 2 has preference of 3, card 3 has preference of 2. Okay, so this queen is willing to exchange a card of higher preference for a card of lower preference. So you can see this card 2 has preference of 3, card 3 has preference of 2. So he can, if somebody gives him a card 3, then he would like if somebody gives him a card 2, which has higher preference, then he would take it for a card 3 which has lower preference. Or if somebody gives her a card 2 for card 1, then also he would take it because it has higher preference. Same for king and jackal. That's what their preferences, the permutations represent. So what you need to find is initially Alice has card 1. Okay. And these three players have all the n cards. Okay. Alice only has card 1, but queen has all the card 1, 2, 3. King also has all the cards 1, 2, 3. And jackal also has all the cards 1, 2, and 3. Okay. Now Alice wants to get card number n. Okay. So he wants to get n is 3 here. So Alice wants to get this card number 3. So how can he get this card number 3? He need to exchange this card 1 with somebody else. And then just keep on this using these trades, he need to get to card 3. So here what he can do. So for queen, you can see that preference for card 1 is the lowest. So she would not be willing to exchange any card for card 1. Okay, so card 1 should have higher preference in order to in order for that person to take it. Okay, so Alice wants to give this card 1. So somebody who has higher preference for card 1 would only take a card 1. So here you can see Jack also has very low preference for card 1, but this king has a preference of 2. So for the king, you can say that since king has a preference of 2 for card 1 and for card 2 he has a preference of 1, so he is willing to exchange his card 2 for card 1 of Alice. Okay, so he would exchange with the king because his card 2 has lower preference. So this way, Alice would get a card 2 in exchange for card 1 with king. Okay, Alice gets a card 2. After that, from card 2, he want to get to card 3. Okay, so which among these three have a higher preference for card 2 than card 3? Here you can see he has higher preference for card 2 than card 3. So using queen, he would get the card 3. So using queen, he would get the card 3. Queen would exchange the card 3 and give the card 2. Okay, so this exchange would be done. Alice gets the card 3. So yes, he is able to get the card 3 using these two traits. So you would print a yes, and the two traits are: first he gets a card 2 from king, then he gets a card 3 from queen. Okay, first he gets a card 2 from queen, then a card 3 from card 2 from king, and a card 3 from queen. So you also need to print that sequence. Okay, in the second test case it was not possible, so you printed no. Okay, so what can you do here is, like, if you analyze this for any, basically for any person. Okay, if you have some random permutation here, you had 132. Okay, if you look at it, what it means that whichever you can arrange them preference wise. First these three cards, 1, 2, 3, if you arrange them preference wise, then like you can see for 1, 2, 3, 1, 2, 3. Okay, let's say you have some random permutation. Okay, you have some permutation of 1, 2, 3, 1, 5, 4. Okay, whatever permutation you have, what does that mean? That means these are the preferences for the cards. Okay, so card 1 has preference of 2, card 2 has 3, card 3 has 1. Okay, so if you arrange them in order, then the lowest preference is preference 1 for card 3. It has lowest preference. Then card 2, the second preference is card 1. Card 1 has the second lowest preference. Third lowest is card 2. Card 2 has third lowest preference. Fourth lowest is card fourth lowest is card 5. So card 5 has the next lowest, and the highest preference is for card 4. So any permutation, like basically what you are doing is just taking the inverse of that permutation. Okay, at index 1 you had 2, at 2 you had 3. So take the inverse. Then uh, 3 was at index 2. So 3 was at index 3 I had 1. So now at index 1 I would have 3. Okay, at index 2 I had 3. So now at index 3, I would have 2. Okay, that way, if you take the inverse of the permutation, you get this order. Now, what does this order mean? It means whenever, like, if you have a car, if you have a card of 1, then if Alice has a card 1, then he can exchange card 1 with any card of lower preference. Now Alice wants to move from card 1 to card n. Okay, and Alice also has preference of lower value, has lower preference than higher value. So he would never move to some, let's say from card 1 he moves to card 3 and then he move back to card 2. That would not never happen. He would only move in increasing order. So from card 1 he may move to some card, let's say 3, then some card 5, then some card n. Okay, that only in increasing order only he will move. So first, if he has card 1, we need to determine that if Alice has card 1, then which all cards can Alice exchange the card 1 with. So that would be determined for all the 3 person. If we arrange it like this, then if card 1 is here, then he can exchange card 1 with all the values before 1. Okay. So for the first person, like let's say this is for the queen. Okay, same for the king and jackal. You would have some order. Okay, there would be some order of the cards for king as well as for jackal. So what you can see is for card 1, you can determine where the card 1 lies in for all the 3. Okay, so you start with card 1, where it lies. Okay, this card 1 can be exchanged with anything before 1, which is greater than 1, not less than 1. So let's say you exchange with 3. Now you can use this 3 to exchange with anything lower than 3. Let's say in king you had 3 here. Okay, let's say in king you had 3 here. So using queen you exchange 1 with 3. Okay, using king you can exchange 3 with some other card. Let's say 4 is somewhere here, that you can do. So that way you need to perform. So you basically need to reach n. Okay, so you need to check if you start with 1, can you reach n? So that can be determined that if you start with 1, you can only reach, so 1 would be somewhere here, maybe 1 is here in here, or 1 is here in this jackal. Okay, let's say 1 is here in king, and in jackal also 1 is here. Okay, and then some random permutation. Then you would say that first of all, if 1 was at the start for every person, you cannot exchange 1 with anything. You will print like no. Okay, but here you can exchange 1. So with whom can you exchange 1? So from 1, you can see you can reach anything less than 1. So you can reach 3 using queen. Using king and jackal, you cannot reach anywhere. So from 1, you can see less than that what all values are there. So 3 is there, so you can reach 3. Now, once you have reached 3, you would check for 3 in all the 3 arrays. So 3 is here in here, 3 is here. Like in this, let's say 3 is somewhere here. So if you check with 3, all values less than 3 are accessible through 3 if they are greater than 3. Okay, so from 3, you won't move to 1 back. You would only go in increasing order. So here, how all those values which are greater than 3, they become accessible now. Same way here, all those values greater than 3, they become accessible now. Let's say some value greater than 3 was uh, 4 here. So now 4 becomes accessible. So once this 4 becomes accessible, now you can check from 4 wherever there is 4. Before that, all become accessible. And once, if in this way, if you reach n, that means this n is accessible. That means you can say that you have reached your final answer. You can say a yes. So, but the problem is if you look it like this, okay, if you start with 1 and all the values before it, all values before it, all values before it, that may go order of n for 1 checking. Then you go for whatever values you got. Let's say you got 3, then check for all less than 3. So every checking would take order of n time, and then you are doing it n times. So that would go n square. Okay, and you can see with the given constraint, n is 2 into 10 power 5, n square won't be accepted. You need to optimize the approach. So what you do is think in the reverse way, that from 1 you need to reach n. So if you want to reach n, first determine from what values can you reach n. Okay. So first you would say that n is 4 here, let's say. Okay. So from what values can you reach this 4? Okay, so this 4 is reachable from all those values which are have priority higher than 4. Okay, so this 4 would be reachable from all those values which have priority higher than 4 in any one of the person higher than 4. It would be reachable for them and has value less than 4. Okay, so for n, obviously all values would be less than n, but when you go lower, then there would be some values greater than n. You won't go reach some x with some value y which is greater than x. You would not go lower. You would always go higher. So basically, if you think in the reverse order, you know that n is reach n is the place where you need to reach. Okay. Now check whether can you first from n you just mark all those. Okay, like what you do is wherever there is n, you mark them as 1. Okay, so you create basically 3 Boolean arrays, let's say. Okay, so wherever there is n, you mark that as 1. Okay, so this place is uh, the place where we need to reach. Okay, okay, so that is okay. Now check whether you can reach there from n minus 1. Okay, so basically finally what you need to check from 1, if you are like from 1, let's say you were able to reach 3. 1 was the minimum. So from 1, if you are able to reach, let's say 3, 2, these are the values you are able to reach. Okay, you can represent them like a graph if you understand it. From you have nodes from 1, 2, 3, 4. Okay, if n was 4, you have nodes like this. So if you have something like this, from 1 you can reach 3. That means you can draw it like this. From 1 you can reach 3. Okay. Now from 3 where you can reach? Okay, from 3 you have 4 below it. 1 from 3 you won't go back. You would only go forward. So from 3 you can reach 4. You can represent it like this. But problem with the graphical approach was that the number of edges would go order of n square. Okay. So if you try to draw a graph like this, that from 1 where all we can reach, at max you can have n edges starting from 1, n edges starting from 2. So it would go order of n square edges. So that was not fine, but still you can optimize it with this thinking. What I'm doing is from 1, you can reach some of the edges which are determined by the positions of 1 in these 3 array. Okay, somewhere 1 is somewhere there. All those values less than 1 would be reachable from 1. So what you say is, if you're starting from 1 and there are, let's say you were able to reach both 2 and 3 from 1, let's suppose, then starting with 1 you can reach these two values only. So you need to make sure that starting with 2 or at starting with 2, if you can reach n, then you can reach n starting with 1 also, you would say. And starting with 3, if you can reach n, then you can reach n starting with 1 also. So if one has some, let's say 2 edges, then you take the or of both, that can you reach n from 2, can you reach n from 3. If you have pre-computed that thing, then you can say that you can reach n from 1 if you can reach n from either 2 or 3, that you can say. So basically from 1, like if you want to represent it like dp, then you would say that dpi represents that can we reach n starting from I. Okay, like you can think of it like a dp state where dpi is can we reach n starting with I. So that can be computed starting with n going to 1. This way we would compute it, because for any I, the transition would be that index we can reach, take the OR of all those. That would be the value for 2. That if we can reach n starting with 3 or with 4, if 2 has edges 2, 3, and 4, then we can say that we can reach n starting with n. If none of them, uh, if the answer for both the DPs are 0, then we would say the answer for this is also 0. So what we can say is, okay, this we can say. So we need to compute this DP from the end starting with n. Okay, so first I would say, like, the base case would be that DP of n would be 1 only. Okay, like starting with n, you can always reach n. Okay, because you are already at n. So starting with n, you can always reach n. So DP of n would be 1. 1 represents yes, 0 represents no. Okay, now if you want to check for DP of n minus 1, how can you check? Then you would check that for n minus 1, you would check the positions of n minus 1 somewhere. Okay, from n minus 1, what all values can you reach? Take the OR of those. Okay, so for any I, we can say that for any I, what would be our DPI? The transition would be that we would check that for, let's say we are calculating for DP2, then for DP2 in the first permutation, we would check all the values less than DP2. So all the values less than 2, having priority less than 2, and having value greater than 2. Okay, those among those, if any of them has a DP, uh, uh, any of those has a DP value equal to 1, then our answer would be 1, otherwise a 0. So for DP2, we can say that for DP, if you are computing DP2, all the values less than 2, among them having value greater than 2. So this 3 is having priority less than 2 but value greater than 3. So if this 3 has a DP value equal to 1, then I would say for 2 also we would have a DP value 1. Otherwise, we would check in the next row. Okay, next row again, like let's say we, okay, let's say we have this test case here. We have 5 and 2, and we had n equal to 5 then. So let's say we have 5 here and 2 and 4 here. Okay, so we would say, like, for DP2, we would check here if any of them has a value 1, then has a DP value 1, then we would say that DP2 has a value 1. Again, here we would check if none of them had a value 1, then here we would check if anything having priority less than 2 has a DP value 1, then we would have its value 1. Okay, otherwise we would check here having value less uh, and a DP value 1, then it would have 1. So what I can say is my transition is like this, that DPI is basically for all the values, like in every permutation. Okay, so for every permutation, we would check uh, for, like, for all j less than I, if any of the, like, if any of the DP. Okay, so this j should, the value j should be greater than I. So if any of the DP j is the position, if it's position of the j. Okay, so if the position of j, I would say, okay, so for any I, like if this is our I, then all those j having position less than here, okay, priority less than this in any of the permutation, but value greater than I. So for all j greater than I, if the position of j is, if the position of j is less than the position of I, then we take the OR with that, okay, and dp of j is equal to 1, then we say that dp of I is equal to 1. So if for any j, okay, so for, we would say for any j greater than I, if we find any one j whose position or priority is less than I, but its dp is equal to 1, then we say that dpi is also 1, because those are the, because if dpj is 1, that means from j we can reach n. Okay, and from I, if we can reach j, what is the condition? That its priority of j should be less than I in any one of the permutation. Okay, should be less than I, and this j should be greater than I. Then we would say that dpi would become 1. So this, I think we can say that this is the transition for our dp in a way. Okay, but the problem is, if you are computing for every j greater than I one by one, if you are checking, again that transition would take order of n time. Overall it would become order of n square. So we need to optimize this thing. So what can we do here is, if you look closely here, okay, let's say what we do is, we initially our dp would be initialized with 0. Okay, what we will do, the problem here was, for any I, if we are going to all the j greater than that and checking for that, that was not feasible. But what I am doing is, I am moving from n to 1, I am moving down. Okay, and I have to take or. So or with 0 is not going to affect my answer. So basically what I would do, I would initialize my dp with zeros, with all zeros. So for all dp 1 to dp n minus 1, okay, all of them would be equal to 0 initially. Only dp n would be equal to 1. Okay, so here we would say that here my n was 5. So I'll say here my dp 5 was equal to 1. So at 5 we have 1 in my dp. At 5 we have 1. But for the remaining values, we'll initialize them with zeros. Okay, so we'll initialize the remaining values with 0. All the dp of 2, that would be 0, dp of 3, that would be 0, dp1, dp4, that would be 0. Okay, now what we would have, okay, if you look like here, if in this representation, if you look what actually my transition is, my dpi is, okay, so let's say I'm computing for I is equal to 4. What is, if I'm computing for I is equal to 4, what is my dp of 4? It is that for 4, all the values having priority less than 4. Okay, these are the values having priority less than 4 and value greater than 4. Among them, we take the or basically. Okay, we are like, if any one of them is having value 1, it would become 1. Basically, we are taking the or. Okay, so what we need to do is, for 4 we need to take the or of the dps, all those dps having value greater than 4. So here value greater than 4 was only 5. So we need to do or with only this. But if we want to do, if we can like, if we, what if we do or with all of those values, does it affect the answer? Because all the values that are less than 4, their dp is 0. So doing or with 0 is not going to affect my answer. So basically, I can say that for 4, what I would do is, I would do or of all the values less than 4. Okay. So if somehow I can compute the or of this range optimally, then my DP would be computed very well. Or, okay, so for 4, we would say that all the values having priority less than 4, do the or of them. That would be the DP state for 4. Or again, in this row also, all the value having less than 4, do the or of them. For this also, all having less than 4. Okay, so basically for 4, if you are selecting, like if you're selecting calculating dp4, then you need to do the or of this and this. Okay, so or of this means, if any one of them has a value 1, then my dp state would be 1, otherwise it would be 0. So when would my dp state be 0? It means all of them are 0, all of them are 0, and all of them are 0, then only it would be 0. So when would all of them be 0? So what I'm doing in order to compute optimally is, I'll, for every this sequence, for every permutation, okay, in this ordering, whatever dp states I'm getting in this, I would keep the minimum index having dp state 1. Okay, the minimum index having dp state 1, that I would keep for each of the 3 permutations. Okay, so I'll store that my mn of 0 is, okay, 0 represents this q. Okay, 0 represents q, 1 represents king, 2 represents jackal. Okay, this is what I'm telling. So I'll say my minimum of 0 is for the permutation for of queen. Okay, what is the minimum index that has a dp state 1? Okay, so minimum 0, initially it would be when I've updated only for dpn. Okay, so what is the position of 5? It is this. So this would be my initial minimum. Okay, so it's this, like here you can index it also. Okay, you can also write the indexing of these positions. Okay, so like this is the ordering. This is the index for the ordering, priority ordering. Okay, so whatever the P of 5 basically would give you the position of 5. So whatever is the position of 5 is 3. So at 3 we have a 1. Okay. So in this sequence the minimum value having a DP state 1 is 1. So initially mn0 this was 1, mn1. Okay. In this sequence what is the minimum index having DP state 1 is this. Okay. So this is 0, 1, 2, 3, 4. Okay. Okay. This is 4. Okay. This was 3. Okay. The minimum index is 3 here. Okay. Here the index is 4. If you write the indexing for this, it would be 1 here, 2 here, 3 here, 4 here, 5 here. Okay. And for this, 5 is at this index 0, 1, 2, 3. Okay. So at the third index, this is the minimum index having DP state 1. So Mn of 2 is 3 here. Okay. So this was green. Okay. Don't confuse it with this. Okay. So these three things we would maintain. And then let's see how I can now compute my transition very fast. What I would say that for any DPI. Now I want to compute DP for 4. What I would do, my DP4 would be that do we have a 1 before this position? So whatever is the position of 4, do we have a 1 here? How can you check fast using this? That if the minimum position where there is a 1 is less than the position of 4. Okay, so here we had a 1 at index 3, which was less than the position of this. Then I would say that yes, it has a 4. And yes, its DP state would be 1. Yes, it has a 1 before its position. Like for this, if you see, the minimum index in this column was here, which was greater than the position of 4. So here we won't, here the OR of this would be 0. Okay, so basically the OR of this whole range can be computed very quickly, that if the minimum index having a 1 is less than the position of this, then I say the OR is 1, otherwise the OR is 0. Very simple. So in order of 1, we are able to compute the DP state if we maintain this minimum. Now, here we see that this OR was 1, so its state became, so we would say that my DP of 4 became equal to 1 now. Okay, so I'll update my DP of 4 as 1. Okay, so this 4 here also, all at all the three places. Okay, this is, I'm writing as DP of the value, so it would be updated at all the three places. So the minimum would also be updated at all the three places. Okay, so here the minimum was at this position. This one got added here. It still remained 3 only. But here, if you see, the minimum index where there is a 1 was at here. Now it has a 1. So for this, the minimum index having a 1 became 2. So this got updated to 2. Okay. Here also the minimum index having a 1 was this. It remained this only. So it would remain 3 only. Okay. Next, I'll compute DP of 3. Okay, next I'll compute DP of 3. So DP of 3 will look at the value 3. Okay, so is there anything having 1 before 3? Nothing. So the minimum index having 1 was here and my position 3 was here. So this was greater. So I'd say a no. Now for this 3, what if we take the OR of these? We have a 1 here. So basically the minimum index having a 1 in this DP was here, which was less than the position of 3. Okay, so here we say yes, our DP of 3 would become 1. Okay, and so once DP of 3 becomes 1, I'll change it to 1. Here also it would change to 1. Here also it would change to 1. Now, along with changing, these three minimums would also get updated. So in this, the minimum became index 0. Okay, so in this, the minimum became index 0. In this, the minimum remained index 2 only. In this, the minimum became this index 2. Okay, so sorry, I did a 0 based indexing here and 1 based here. So let's keep it consistent only. Uh, okay, what we want to do is let's do a 1 based indexing only. Okay, for the example only. I hope that is clear. Okay, so now the new minimum is not 0 but 1 in this. Okay, and in this my minimum is 2. In this my new minimum is index 2 only. Okay, this from 3, the new minimum is index 2. Okay, so this way in minimum is updating and my DP transitions are being calculated in order of 1 only if we are storing the minimum index having DP state 1 in this sequence. Okay, in this ordering, preference ordering. Okay. And one, so this way we can easily conclude. I hope this logic is clear. And we also need to answer our basically the sequence, the path through which we would go reach n. So while storing the DP state, we also need to store how we are reaching this state. How, if a DP state is 1, then how are we reaching? So DP state 1 represents that we can reach n starting from I. So if we can reach n starting from I, then how from I, where do we reach so that we reach n? So basically, whenever you like, here you were computing for DP2. So DP3 you were computing. So what we did for DP3, where do we got a yes? Here we didn't got a yes, but here we got a yes through this 4. Okay. So the minimum index here was less than the position of 3. Okay. So at minimum index, whatever was the value, it was 4. So from 3, if we transition to 4, then from 4 we can reach n. So we would store 4 as the parent of 3. Okay. So we would store 4 as the parent of 3. And in which permutation we did that? In the king's permutation we did that. So we would also store the king along with that. Okay. So this parent thing also we would store, so that finally when we want to compute our answer, we would just check the uh, we would start with, we would just check if my DP of 1 is 1, then yes, we would answer yes that we can do. And if my DP of 1 is 0, that means no, we cannot reach n starting with 1. We would answer no. Now for the yes case, we also need to print the sequence. So how do we print the sequence? For that, we go to the parent of 1. That how did we reach a yes in 1? That was through the parent of 1. Okay. Now for parent of 1, so for while calculating DPI only, if you store the parent, okay, that way, whatever was the parent of 1, if it was parent of 1 was, let's say, some J, then we would go from J, we would go to the parent of J. Okay. Let's say we reach some, this was J1. From J1, the parent of J1 was, let's say, J2. Then the parent of J2 was, let's say, J3. And through that, after some value, whenever this Ji becomes equal to n, we stop there. Okay. So we have reached n. Okay. That way, like recursively or one by one, we'll go from parent to parent and we'll get to know that from 1, if how do we have to move in order to reach n. Okay. And along with this parent, along with storing the parent, we would also store whether we are using king, queen, or jackal. Okay. So using 0, 1, or 2 in pair, we would also store that thing. Okay. We'll look at the code, how I'm implementing that. So I hope it is clear to you, the logic, that how I'm computing this DP state optimally. Okay. So how this DP state is computed optimally by storing these 3 minimum values. Okay. In this ordering, if we store the minimum index having a 1, then we can easily compute the transition in order of 1. Okay. And in order to store our answer, we'll store this uh, vec parent vector. Okay. So let's look at the code so you'll understand more clearly what I'm trying to say. Okay. So here we took the input. Okay. So while input, we need two things. We are given these 3 permutations. Okay. So that I'm taking in P. Okay. So P is a vector of size 3 cross n. Okay. So P of 0 would represent the first permutation. This is represented by P of 0. P of 1 represents the second permutation. P of 2 represents the third permutation. That way I'm taking the input. Okay. So I from 0 to 3, J from 1 to n, C in Pij. Along with that, if I also need to get this ordering. What was this ordering? This was the inverse of P. Okay, so if this was the P, when we take the inverse of P, we get this ordering, the ordering of the priorities, which value is at priority 1, which value is at priority 2. That value thing where is actually the inverse of this vector p, with the permutation p. So for inverse, we take this val variable in which we store the inverse of p. Okay. So for storing the inverse, what we do for the this first I would remain same. That would be 0, 1, or 2, representing whether it is queen, king, or jackal. Okay. So val of I is okay. For I, val of I would be I only. But here we were taking whatever value we got, that was p of ij. But to make the inverse, that value p of ij would be at the index, and the resultant would be the index j. Okay, so that way we got the inverse. So val of I comma p of ij is equal to j. Okay, so that way we took the inverse. So we got the value at priority j. Okay, so whatever is the priority, okay, the value at that is j. Okay, this represents the priority of j. This represents the value at whatever is the priority of j. The value is j there. Okay, so this way I got the inverse. After that, I took this minimum vector of size 3. Okay, I initialized it with n plus 1. Initially, when all of them are 0, I'm telling that this n plus 1 index has a value 1, that I'm supposing. Okay, but basically I'm initializing it here. Okay, I'm initializing all of them with the position of n. This is the position of n. Okay, so position of 5 was 4 here. Okay, so here we have initially we have dp of n is equal to 1. This was our base case. Okay, so this how we are doing this. So all the positions where there is n, we initialize a 1 there. Okay, 1, 1, 1. All the positions where there is n, all the remaining positions would be 0. So my minimum would be updated like that. The minimum index where there is a 1 would be the position of n in all the 3 permutations. So in all the 3 permutation, my minimum of for the permutation I is the position of n. Okay. So this I've initialized, and I've initialized this parent vector as a vector of pair. Okay, so this is a vector of pair. Okay, so in pair, I've initialized it with -1 comma -1. So if it is -1 comma -1, it just represents my DP state is 0. From there, I cannot reach n. Okay, otherwise I'll store. So initially it would be -1 comma -1, all DP states are 0. While calculating, I'll in the parent vector, I'll store which one is the parent of which one if the DP states become 1. So how do we get the 1? Okay, now here, like initially I would store f equal to 0. I'll run a loop from 0 to 3. So if my minimum of I is greater than p of ij, as I explained you how my transition is working, that for if I am to calculate for dp of I, so let's say I equal to 2. So for 2, we'll check if I get the minimum index having a 1 is before this position, then I would say a yes. If it is not, if it is above this position, then I'll say a no. So I'm telling if the minimum is above the position of j, then I do a continue. Okay, so it's a 0. Okay, and if not, if I don't do a continue, that means I got an answer. Okay, I got my DP state became yes. So I did f equal to 1. F is actually my DP state. So f is equal to 1, and I break out that even if in one permutation I got a yes, then I don't need to check the next permutations. I got a yes. Okay, so I got a yes, and in my parent j I would store. Okay, so for j, from where did I get? Okay, so like for this 3, from where I got a yes, I got a yes from this 4. This 4 was the position, the value at the minimum index. Okay, so the value at the minimum index was this 4. Okay, so this 4 would be assigned as the parent of 3. Okay, so parent of j is assigned at the value at the minimum index, comma I just denotes 0, 1, 2, 3, whether queen, king, or jackal. If we are at queen, it would be I equal to 0, here I equal to 1, I equal to 2. Okay, so that way I'm storing the parent f equal to 1 and break. Okay, and if f remains 0, that means our DP state was 0, we do a continue. Otherwise, I would have to update my minimum. My DP state became 1. So if let's say at 3, my DP state became 1. So here I have to get a 1, here I have to get a 1, here I have to get a 1. So update all the minimums for the 3 because I got a 1 here. Okay, so the minimum index having a 1, is now updated with the position of j. This can also be one of the minimum index. So my minimum index is updated here. Okay, I hope this is clear. My transition is done. Okay, I need to compute my answer. So if my parent of 1 dot first is -1, that means my dp of 1 is 0, then I see out a no. Okay, as I told you, if my dp of 1 is 0, then I see out a no. Okay, and I return. Otherwise, I see out a yes, that yes, if some parent exists that my dp state is 1, I see out a yes. Then how I compute my answer? I go to parent of 1, okay, then parent of j1, parent of j2, that way up till ji becomes equal to n. Okay, so I initialize j equal to 1 until j becomes equal to n. What I do? I do j is equal to parent of j. Along with that, in the answer, I push back the character at, okay, so in my parent, what I was storing in dot second, I was storing the I representing 0, 1, or 2. So at in ch, I have just stored 0 represents q, 1 represents king, 2 represents j. So I just convert it into character because finally I need to print the characters either k or q. Okay, so ch0 would be q, ch1 would be k, ch2 would be j. So ch of whatever is the index, so parent of j dot second, parent of j dot second gives me that index I, which one is being used, 0, 1, or 2. Okay, and that 2ch would give me the character, queen, king, or jackal, and comma. The second value that we need to print in the answer is the through which card are we doing, like through which, basically value through which we are doing. So parent j dot first, just the parent of that. Okay, that one by one we would print. So that I stored in my answer, and in j I shift j to parent of j dot first. Okay, so until j becomes equal to n. This way I got my answer in my answer vector. I print the answer dot size and all the values of it dot first, it dot second, all the individual values of my answer vector. So this way, this whole thing got printed. Okay, I hope this problem is clear to you now. Okay, if you look at the time complexity of this input was 3 into n. Okay, so this was order of n. This minimum is a vector of size 3. This parent is size n. Okay, this is running 3 times, so it's order of 1, running only 3 times. Okay, this loop is running n times. Inside we have this order of 1. This is running 3 times. These are order of 1 operations, run 3 times. Okay, this is also order of 1 operation, run 3 times. So these are all constant time operations, 3 times, 3 times, maybe 6, 8 times. Okay, so constant time we get n times constant operation, so order of n. This would be order of n. Okay, this is our constant time operation. Okay, this while loop would run at max n times. Okay, at max n times this would run, and my n size of my answer would be at max n. Okay, so my overall time complexity would be order of n here, n here, n here, and n here. Okay, so overall it would be order of n only. Okay, and if we look at the space complexity, again for space complexity, we have only vectors of size like 3n, 3n, okay, size 3, n. Okay, so these vectors are only used of size n. This would be also at max n. So order of n space complexity. Okay, I hope this problem is clear to you. The main thing to understand here, how do we optimize our DP state using this minimum thing? Okay, so using this minimum thing for any index, we need to take the OR of all these values that I'm storing by the minimum index having a value 1. So that was an interesting thing to learn. Okay, so I hope this is clear to you, and thank you so much for watching. Goodbye.